Hello! In this video, we are going to prove the following theorem. Suppose Zn is a sequence of complex numbers, and suppose Z is a complex number. If Zn converges to Z, then 1 plus Zn over 2 to the n to the power of 2 to the n converges to e to the Z. Now, in a previous video, we proved a really similar result, which is the following. We proved if Zn converges to Z, then 1 plus Zn over n to the power of n converges to e to the Z. And the proof of this is actually going to be really similar to the proof of this. So I'll leave a link in the description below to the video where we prove this. Now, in the video where we proved this, we first proved the following preliminary result. Suppose Z and W are complex numbers, suppose n is a positive integer, and suppose capital M is a real number, such that absolute value of Z and absolute value of W are less than or equal to capital M. Then, this inequality is true. Now, in proving this theorem, let's remind ourselves about subsequences. If you recall, if a sequence of complex numbers is convergent, then all of its subsequences are convergent, and they converge to the same value, right? We proved that for real numbers. In fact, the same argument proves that it works for complex numbers. And so, in that case, since we know 1 plus Z over n to the power of n converges to e to the Z, it follows 1 plus Z over 2 to the n to the power of 2 to the n will also converge to e to the Z. Because this guy is really just a subsequence of this. Right? So now, let's get into proving this theorem. And to start out the proof, let's suppose Zn converges to Z. The whole goal from here is to prove that this guy converges to e to the Z. Now, since Zn converges to Z, it follows that the sequence absolute value of Zn must converge to absolute value of Z. And the sequence of absolute value of Zn is a sequence of real numbers. And we know that every convergent sequence of real numbers is bounded. So this sequence must be a bounded sequence. So we should be able to find a real number that is greater than or equal to every term of this sequence. And so we'll call that real number capital M. Now, certainly, because we can find a real number that is greater than or equal to every term of this sequence, then we can also find a real number that is not only greater than or equal to every term of this sequence, but also greater than or equal to absolute value of Z. So we'll assume that the real number capital M that we found is also greater than or equal to absolute value of Z. And now remember, the whole goal is to prove that this sequence converges to e to the Z. And to show that, it suffices to show the following. It suffices to show that this sequence converges to 0. Because what happens if we have shown that this sequence converges to 0? Well, since this sequence converges to 0, and this sequence converges to e to the Z, it will follow by the addition rule for limits that this sequence plus this sequence converges to 0 plus e to the Z, which is equal to e to the Z. But this sequence plus this sequence is precisely this sequence. So we will have shown that this sequence converges to e to the Z, and we will be done. So yeah, that's why it's sufficient to show that this sequence converges to 0. So then, how will we show that this sequence converges to 0? Well, by definition of the limit of a sequence, to say that this sequence converges to 0 means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of the nth term of this sequence is less than epsilon. So to prove that, let's first give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of the nth term of this sequence is less than epsilon. So how do we find an appropriate value for capital N? Well, we're going to use the fact that we know Zn converges to Z. And since Zn converges to Z, we can find capital N in the following way. Since Zn converges to Z, there must exist a positive integer capital N such that for all n greater than or equal to capital N, the absolute value of Zn minus Z is less than epsilon over e to the n. So all we've done here is we've applied the definition of the limit of a sequence, right? The definition of what it means for Zn to converge to Z to the positive real number epsilon over e to the n, right? Because what does this mean by definition? It means the following. It means this, right? And this statement works for every positive real number. So in particular, it must work for the positive real number epsilon over e to the n. So we took epsilon to be e to the n, and it follows that this statement is true. And that is precisely what we've written here. Right, and so the claim is, with this choice of capital N, we can show for all n greater than or equal to capital N, the absolute value of the nth term of this sequence is less than epsilon. Right? So to prove that, let's give ourselves an arbitrary n greater than or equal to capital N. And now let's show that the absolute value of the nth term of this sequence is less than epsilon. Well, first we write out the absolute value of the nth term. And now, to show that this guy is less than epsilon, we're first going to use this preliminary result. Now, we're going to take Z to be Zn, we'll take W to be Z, we'll take N to be 2 to the N, we'll take capital M to be the capital M that we have in our proof. Right? And with our choice of Z and W, we know that absolute value of Z is less than or equal to capital M and absolute value of W is less than or equal to capital M. That's precisely what this third line is saying. Right? So, with these four choices, we have that this inequality is true. But notice, with these four choices, the left-hand side of this inequality is precisely this. And it's less than or equal to e to the capital M times absolute value of Zn minus Z. And then let's remind ourselves how we chose capital M, right? We know for all n greater than or equal to capital N, the absolute value of Zn minus Z is less than epsilon over e to the n. So this statement works for all n greater than or equal to capital N. So in particular, it must work for the n that we introduced here. So taking n to be n, we have that this inequality is true. And therefore, this guy must be less than e to the m times epsilon over e to the m, which is equal to epsilon. And so we have shown that the absolute value of the nth term of this sequence is less than epsilon, which is exactly what we wanted to show. And that means we have shown that the sequence converges to 0. But this was enough to show that this sequence converges to e to the z. And so this completes the proof. Now, as we reach the end of the proof, we realize that there's nothing really special about 2 to the n. So this fact could actually be generalized to any increasing sequence of positive integers. So you could replace 2 to the n with 3 to the n, it would be true. You could replace 2 to the n with 5n plus 7, would be true. Right? As long as you have a strictly increasing sequence of positive integers, it will also work. Because the only thing that made 2 to the n work was that this subsequence will converge to e to the z, right? And so yeah, that's pretty much it for this video.